Today we're going to be talking about antiderivatives. So antiderivatives are the undo function for derivatives. So in mathematics, it's been our habit to teach you an operation and then teach you how to undo the operation. For example, first grade, you learn to add. Second grade, you learn to subtract. Third grade, you learn to multiply. Fourth grade, you learn to divide. Same thing as raising to powers, then taking radicals. We taught you exponentials, e to a power, then we taught you the natural log. So we've learned derivatives. We now need to learn how to undo a derivative or take an antiderivative. So an antiderivative is the undo operation for a derivative. Now, when would you maybe want to do something like this? For example, it could be something like you have the position function and a velocity function and an acceleration function. But in the beginning, you're not given the position function at all. Instead, you're given the acceleration function and a point on the initial velocity. So you're able to take the antiderivative of the acceleration to get the velocity function up to a constant. And then you use that initial condition of the initial velocity to pin down what the constant is. Then you can take the antiderivative of the velocity function, and that will give you the position function. So we've taught you to take the derivative, and now we're teaching you to undo the derivative by taking the antiderivative. Now, this is an extremely important topic. I can't stress enough how important this is. You will be doing this on a daily basis from now on. I can't say that this will be used half the time or 75% of the time, because it's pretty much used 100% of the time. There's almost no section, well, there is no section in Calculus 2 where you don't have to take an antiderivative. And in Calculus 3, it continues to be the case that antiderivatives are hugely important. So this is a topic that you need to learn with at least 95% accuracy, if not higher. So what we're going to do is we're going to start by talking about a function. And let's suppose that we have this function called lowercase f, and we want to find a function where when we take the derivative of that function, we get lowercase f. We call this function generally uppercase f as the antiderivative. So we call uppercase f an antiderivative of lowercase f if when we take the derivative of uppercase f, we end up with lowercase f. So the derivative of the antiderivative is equal to the original function. So this is the derivative of the antiderivative. And that relationship is at the core of what an antiderivative is and how it works. So an antiderivative then means that you have undone the derivative here, and then you take the derivative again. So it's like going nowhere. You get back to the original function, which is f. Now, are there any other functions that would serve as antiderivatives of lowercase f? And the answer is yes, there are lots of them. In fact, there are infinitely many. Anything that is of the form the antiderivative function plus a constant, where c is a constant, would also serve as an antiderivative. And the reason is when you take the derivative of the constant to get back to the original function, the derivative of the constant is 0. So you end up with the derivative of uppercase f again, and that leads to lowercase f. So what we find then is we have a family of functions, a group of functions that are identical up to the constant, where the derivative of them gives us this lowercase f. And we can think of it as the reverse of antidifferentiation. So let's think about, for example, the function x squared. And let's think about the function 2x. So if we let 2x be our lowercase f, and we ask ourselves, the derivative has already taken place and the result was 2x. What could the original function have been? What would I take the derivative of and end up with 2x? So I took the derivative of something and I got 2x. What's f? Well, if we think about the power rule, then we can easily come up with the function f of x equal to x squared, because we know by the power rule that the derivative of x squared would give us this 2x. So x squared is an antiderivative of the function 2x. So it undoes the derivative. So 2x is what resulted after the derivative was done, and x squared is the function that was there before the derivative was done. Now, that's not the only one, because we could also use, for example, x squared plus 5 or x squared minus the square root of 2. The derivative of both of these functions would also lead to 2x, exactly 2x. So again, we see that we get a class of functions, and a class of functions can be written generically as x squared plus c for some constant value c. Any real number at all will do. Now, we know from the corollary 2 of the mean value theorem that if f and g are differentiable functions so that their derivatives are equal, then they vary by only a constant. So that means that there are not any other antiderivatives except ones of the form x squared plus c. So all of the antiderivatives for 2x have that basic format. All the derivatives of 2x have to be of the format x squared plus c, right? That's guaranteed by corollary 2 of the mean value theorem. Now we want to talk about the general form for an antiderivative. We're going to let uppercase f be an antiderivative of lowercase f over some interval I. Then we can say for each constant c, the function f of x plus c is also an antiderivative of f over I. If g is an antiderivative of f over I, then there is a constant c for which g is equal to f of x plus that constant over I. In other words, all the antiderivatives have the same format, and they differ from one another always by a constant. So remember when we talked about this in corollary 2, we gave the example of the parabolas which had been shifted up and down, but were basically the same size and same shape, just shifted up and down. So when we're looking at those, that gives a family of functions. Now, the definition of the antiderivative is a function uppercase f, and it is an antiderivative of lowercase f if when you take the derivative of uppercase f, you get lowercase f for all the x in the domain of the function lowercase f. So again, f is an antiderivative of lowercase f if the derivative with respect to x of uppercase f is equal to f of x for all the x. Remember that upside down capital A stands for all x in the domain of lowercase f. And you can think of that as an undo function for the derivative, and that's basically what it is. So we're going to practice taking the undo function for the derivative. We're going to practice it a little bit, and then we'll be looking at some other values, other ways of notating the antiderivative function. Okay. So the first example is this one. Find all antiderivatives of f of x equals sine x. So when you're thinking about this, we need to think about how do I get an undo operation that would give me sine. So I have a function. I took the derivative of it and I got sine. What was the original function? How can I undo that operation of the derivative that was done? So when I'm thinking about that, the derivative of something gives me sine. Well, I know the derivative of cosine is negative sine. So other than the negative, that's the right value. So I need to multiply cosine by a negative. So I say that the uppercase f of x, the antiderivative function, is negative cosine of x. Why? Because when I take the derivative of the antiderivative, then I will get back the lowercase function f. And that gives me sine of x, right? So uppercase function, negative cosine of x, that is the antiderivative. Okay. Are there any questions, or what questions do you have about this? No questions so far?
You were saying lowercase f of x is after we already took a derivative?
Yes, that's correct. I'm just having to think to make sure I'm interpreting what you're saying correctly. Yes, that's correct. Lowercase f represents the result after you've already had a derivative done. Okay? All right.
I do have a question. Is there any way to, instead of being like uppercase F, like any notation, different notation?
Yes,
like
there
all
is.
my F's are the same. So like
yes,
it's really
yes,
hard
all
for
your
me.
F's
Are the same, yeah.
That's a good point, Juan. Some people, all your F's look the same, so this is not going to be a good notation for you. There is, and that's perfect timing because we're about to talk about it. It's called an indefinite integral, and it's using the integral symbol. So this is the formal notation that we use to represent antiderivatives. We do not actually use uppercase F, except in theory and explaining it in the theorems. So in practice, we use the indefinite integral notation that you see right here. And what we're going to do is we're going to define the different parts of this so that you can understand what is happening. The result of the notation on the left is the antiderivative function up to a constant. So this representation on the left represents the operation that undoes the derivative. So this notation here undoes the derivative. Right? Now let's pick apart this notation, and I'm going to write it a little bit larger off to the side so that we can point out different parts of it. So we have this symbol right here, which is an elongated S. It actually stands for sum. That's where it came from. And we'll learn why that happened probably later today or next week. Depends on how far we get. So we've got this elongated S. Now, if you were writing on lined notebook paper, which you should not be because it is neurologically damaging to your ability to do mathematics and not make careless mistakes, you should be working on completely blank paper. It is neuroscience, not rocket science. But if you were, the symbol would extend both above the upper line and below the lower line. All right. And then the f of x, which is the function you're trying to take the antiderivative of, would fit inside the symbol, and it would sit on the lower line. So notice the f of x is not even with the bottom of the symbol, all right? So these are kind of tricky things that you need to learn as you're doing it. It's actually sitting in the middle of the symbol. So f of x is the function that resulted from having done a derivative. Then there's this tiny little space. It's not a big space. It's probably not even a full space, but there is a bit of space. And then there's the differential dx. Dx indicates the derivative with which the derivative with, how can I say this? Dx represents the variable that the derivative was taken with respect to. You had to some function, you took the derivative of it, you got lowercase f. When you took the derivative to get lowercase f, it was with respect to x. If it had been with respect to t, then this would be a dt instead. All right. So let's label the different parts of this. This is the differential right here. It indicates what derivative was used, what variable was used in the derivative. This f of x part right here has a name as well. It's called the integrand. All right. It's common in mathematics to stick an AND or an END on the end of the basic word in order to define what's inside. So when we're talking about subtraction, we have a subtrahend. When we're talking about multiplication, we have a multiplicand. When we're talking about division, we have a dividend. When we're talking about what's under a radical, we have a radicand. And when we're talking about what's inside the integral symbol, we have an integrand. So this symbol right here represents what's called the indefinite integral. Now you may be wondering, why is it called indefinite? It's indefinite because when you're done, you're going to get the antiderivative function, but only up to a constant. So you won't be able to pin down exactly what the original constant was, because when you took the derivative originally, if there were a constant, it zeroed out and disappeared. So when you undo that operation, you can't come up with what that constant originally was, right? So imagine, for example, that you had x squared plus 5, and you took the derivative of it. So you got 2x, and then you want to undo the derivative of 2x with respect to x. You're going to get back the x squared, but there's no way for you to know that the original constant was 5. For all you know, it could have been 2 or square root of 10 or some other value. So there's no way to reproduce that constant. So it's not a definite integral, it's an indefinite integral. And the symbol right here is called an integral. All right. Okay. So when we're looking at this constant that you see right here is often called the constant of integration. And this f of x that you see over here, this is the antiderivative. So this is actually quite a bit of notation and quite a bit of definition. So let's go over it one more time and make sure that we're following what we're doing. This elongated s extends above the line and below the line. The integrand, which is the original function that the derivative has already taken place, f of x, is written on the line, which means it's above the lower curl part of the integral symbol. And then it's next to the differential. The differential tells you which variable the derivative was taken with respect to, so you know which variable to undo the derivative with respect to. And this represents the antiderivative operation. The whole thing is called an indefinite integral. The elongated s itself is called an integral for short. All right. And this results in the antiderivative function, uppercase f of x, up to a constant of integration. Now, the problem is when you take a function, x squared plus 5, and then you take the derivative of it, and this, of course, becomes our f of x because the derivative has already taken place, so that we get 2x. And then you take the integral of 2x, and you want to undo the derivative with respect to x, you can only get back x squared. You may suspect there was a constant, but when you took the derivative of 5, it became 0. So there's no way of knowing what the exact constant was, or even if there was a constant, it could have just been 0 itself. Now, looking at the next part, we have a little bit more terminology. Given a function lowercase f, the indefinite integral of lowercase f, which is denoted with that integral notation of f of x dx. And again, notice that the f of x dx is sitting in the middle of the integral symbol, is not even with the bottom, is the most general antiderivative of f. If uppercase f is an antiderivative of lowercase f, then the integral of f of x dx is equal to uppercase f of x plus a constant. That's just basically going through and stating the same things that we talked about in the image above. Now we can talk about the integrand, the variable of integration, and the constant of the integration. The integrand, remember, is the part that's in the middle. All right, the integrand is the f of x, which is the function on which the derivative has already been done. So in our case here, the 2x. The differential is dx, and the variable of integration is x because x is the variable in the differential. So the differential indicates which variable to take the antiderivative with respect to. Now, there are some students in some classes of calculus that get very lazy about writing the differential. I am an absolute stickler about writing the differential. You will write the differential every time, or you will suffer the loss of 30% of the credit. It will kill your grade, all right? So you will not be writing the integrand without the differential. Without the differential, you don't know what variable to undo the derivative with respect to. It's very important. Now, why am I such a stickler for it? When you get into calculus 3, you get into multivariable calculus. In multivariable calculus, you may have 2 or 3 independent variables, x and y or x, y, and z. And you need to know what the differential is to know which one you're doing the antiderivative of at that particular moment in time. Without the differential, it's impossible because there are multiple independent variables. Okay, let's now move on to looking at the picture of the family of antiderivatives. So here's a good picture of what the class of antiderivatives would look like. So again, here are a lot of different functions, and basically this relates to college algebra or the algebra you did in high school, what you learned there about shifting graphs up and down. So these are vertical shifts of the graph x squared plus 1, x squared plus 2, x squared minus 1, x squared minus 2. But they also represent a family of antiderivative functions up to the constant plus c. All right. So when we're given an antiderivative, we get the basic shape, but we don't know the plus c. So it could be any one of an infinite number of different functions, all differing only by the vertical shift. Now we want to talk about the power rule for integrals. This was really the first rule that we learned when we took derivatives, was the power rule. So it makes sense that we're going to undo this one first. So the first thing I want to do is I want to practice taking the power rule again so you remember what we did. So we're going to start on the derivative with respect to x of x cubed. And when I take the derivative using the power rule, remember we bring the 3 to the front, and then we subtract 1 from the power, and that gives us 3x squared. Does everybody remember the power rule? By now you've been doing it so often it's probably just instinctive for you. You don't even have to think about it very much. It just sort of happens. So when we're doing this and we want to undo the power rule, so we imagine that we're undoing the power rule on something, what would we do instead? We would instead take the function that is the integrand x to the n, we would add 1 to it and then divide by the new power. So for example, if we had the integral of x to the 4th antiderivative with respect to x, then we would take x, we would add 5 and divide by the new power of 5, and then it would be good up to some unknown constant plus c. Right? So we're undoing the operation of the power rule. The power rule, we brought it to the front to multiply, and then we subtracted 1 from the power. So here, in order to undo, we have to add 1 to the power first, and then divide by the new power, all right? And that undoes that operation. Now, there are many, many common ones that we can see, common indefinite integrals and their differentiation formulas. Well, before we do that, let's go ahead and practice on the one we have here, which is 3x squared dx. Now the 3 is a constant, and it's just going to follow along like constants do in just about all of our operations, whether it's a limit or a derivative or an integral. The constant can be pulled out of that operation. So we can do the inverse, or rather the power rule for integrals. So we're going to take the second power, we're going to add 1 to it, and then we're going to divide by the new power up to a constant. 2 plus 1 gives us 3. So this gives us 3x to the 3rd divided by 3 plus c. The 3's cancel, and we get back the original value that we had up here that we took the derivative of, and that gives us x cubed, but only up to a constant. Okay. Now, here are some of the relationships. Now, I have had students ask me, you really expect me to memorize all this? Well, yeah, I do. But you already know it, all right? You've already memorized these. You've memorized them in their opposite form. So now all you have to do is memorize them in the antiderivative form. So I have the two forms up here. I have the differentiation rule on the right, and I have the indefinite integral rule on the left. So for example, over here, if I take the derivative of some constant times x, like 2x, if I take the derivative of 2x, I get 2, right? Take the derivative of 2x, you get 2. Well, if I integrate 2 with respect to x, it's going to replace that x, and I'm going to come up with 2x plus a constant, right? So for example, and I don't know if it's going to write in here or not, we'll see. If I take the derivative with respect to x of 2x, I get 2. So over here, if I integrate 2 with respect to x, I can think of this as 2 times x to the 0. Now, why x to the 0? And it erased it. I knew it wasn't going to keep it in there. It has to be a picture for me to be able to write on it. So let me write it up here. The integral of 2x to the 0 dx. Why x to the 0? Anything to the 0th power other than what? Anything to the 0th power is 1 except
0.
0. 0 to the 0 is indeterminate. Thou shalt not divide by 0, and the 0th power represents dividing the base by itself. So I can represent this as 2x to the 0th power because this represents a 1. And then I can apply the power rule. Add 1 to the power and divide by 1. And so this will give me 2x to the first plus a constant. So you already know this rule. You know this rule in this form over here, the differentiation rule. You just have to learn to undo it. Basically, most students just memorize that the integral of a constant is the constant times x, or the constant times the variable of integration if it's different than x. The second rule down here, this is the power rule. So this is the power rule right here. Power rule for integrals on the left, power rule for derivatives on the right. And we just learned the power rule. This is a really important one. This one probably gets used probably the most often. All right, so it gets used all the time. Now, this next one is important because it is the one exception to the power rule. All right. Why would it be an exception to the power rule? What is it about 1 over x dx that would make it an exception to the power rule?
Divide by 0.
Bingo. Juan has it in 1, division by 0. If we think about the integral of 1 over x dx as the integral of x to the negative 1 dx, if you apply the power rule wrongly, you would get x to the negative 1 plus 1 divided by negative 1 plus 1. And there's your 0 right there. That would be division by 0. So this would be wrong. There has to be another way to do this one, which of course there is. If you look at the derivative side, you'll recall that the derivative of natural log is 1 over u times the derivative of u. So this 1 over u is exactly what you have here. So the integral of 1 over x is the natural log of the absolute value of x. Now we do have something present on the left that we didn't on the right, and that's the absolute values. The derivative of natural log is 1 over the argument, but when you undo it in the antiderivative, it's not clear whether or not the argument is strictly positive. So to force it to be strictly positive, we put absolute values around them. And I am a stickler for that too. I'm not quite as serious about that one as I am about the differential and the plus c, but I am pretty serious about it nonetheless. So make sure you put absolute values around the argument to natural log. The next one's pretty obvious. The integral of e to the x dx is e to the x plus c, because the derivative of e to the u is e to the u times the derivative of u. Now, you'll notice that the formulas on the left do not invoke the chain rule, and the formulas on the right do invoke the chain rule. So we will have to learn another method called U substitution that will help us to deal with undoing composition. So we will learn it, but it will not be until section 5.5. So it's quite a ways down the road. For now, we're going to be dealing with very simple arguments of just the variable. What about the integral of cosine of x dx? I would say that the next three mess up students more than anything else. They just drive them crazy. They've just gotten to where they've memorized that the derivative of sine is cosine, and now I'm asking them to go backwards. And it sort of just messes up everything, all right? They've just barely memorized one direction, and now I want them to go backwards. But if the derivative of sine is cosine, then if I undo the derivative on cosine, I should get back sine. So the integral of cosine of x dx is sine of x because the derivative of sine gives me cosine. So if you take the derivative of the result, you should get the integrand. The integral of sine of x dx is negative cosine of x because the derivative of negative cosine is positive sine. The integral of secant squared of x dx is tangent of x because the derivative of tangent is secant squared. If you think of it that way, it may be a little bit easier. If you continue to think of it in terms of derivatives, it might help you at least this semester. Now, as you get into calculus 2 and 3, if you're going that far, you will start to think in terms of the integral, and then you'll get the derivative messed up. So it does take some time to get them both down really well and separate. And then we have the last two. The integral of cosecant cotangent is a negative cosecant squared, because the derivative of negative cosecant of x is, did I say squared? I meant negative cosecant x. The derivative of negative cosecant x is cosecant cotangent of x. The integral of secant x tangent x is secant, because the derivative of secant is secant tangent. We have another page. We have one more trig integral, which is the integral of cosecant squared, which gives you negative cotangent, because the derivative of negative cotangent is positive cosecant. These last three here are the inverse trig integrals. We will learn another way of doing these in calculus 2, where you do not need to memorize a formula. And in fact, these are the three that I do not expect you to memorize. All right. So you're going to memorize down to here. And if you need the last three, I'll give them to you. All right. So if you need the last three, I'll give them to you. And again, in calculus 2, you'll learn another technique of deriving these formulas called trig substitution, and that will let you find the values without having to memorize a formula. Let's go ahead and practice the first example here. It says, show that uppercase f of x is an antiderivative of lowercase f by showing that the derivative of uppercase f gives us lowercase f. This is a pretty straightforward, just prove that it's the antiderivative. So we want to prove that f of x is an antiderivative, not the antiderivative. There are infinitely many up to constants. So it's an antiderivative of lowercase f of x. So I take the derivative of uppercase f of x, which is the derivative of 5x cubed plus 2x squared plus 3x plus 1. And when I take the derivative of that, I get 15x squared plus 4x plus 3, which is equal to lowercase f of x. And that's my proof. So again, you're simply proving that it is an antiderivative by taking the derivative of it and getting back f of x. Okay. We'll practice this on one more problem. This is actually a quite difficult problem to integrate directly without knowing what the result is. This is one that we will not be able to do this semester. In fact, this will have to wait for integration by parts in calculus 2. So this is a more difficult type of integral. We will not learn how to integrate it this semester, but we can prove that it works. So we need to identify the different parts that we have going on here. So our lowercase f of x is the integrand x cosine of x, and our antiderivative function up to the constant is what we get coming out of the integral, x sine of x plus cosine of x. So we want to prove that the derivative with respect to x of f of x, does that equal lowercase f of x? And it should, right? If f of x is uppercase f is an antiderivative of lowercase. I'll be very glad when I can stop saying uppercase and lowercase. So we'll take the derivative of x sine of x plus cosine of x plus this constant. I've got multiplication between x and sine x, so I'm going to have to invoke product rule right here. So when you do the product rule, remember that you're going to have f prime g plus g prime f. So this is going to be 1 times sine x plus cosine x times x, which I'm going to move to the front, plus the derivative of cosine of x is negative sine x, and the derivative of the constant is 0. So I have sine x plus x cosine of x minus sine x. The sine x's cancel, and I end up with x cosine of x, which is equal to lowercase f of x, which proves that this is an antiderivative. Now we want to go through some of the properties of antiderivatives. As you might imagine, we need to talk about how to deal with constants, how to deal with addition and subtraction. We are not actually going to be able to talk about how to deal with multiplication and division. It turns out that multiplication and division inside an integrand are the most difficult things to deal with. And you could spend entire courses going through techniques of dealing with them. And in fact, you'll spend a third of your time in Calculus 2 dealing with either multiplication and division inside the integrand. All right. So they're quite difficult, and we'll not deal with them here. We will, however, deal with sums and differences and constants. So if I have f of x plus or minus g of x, inside the integrand, I have a sum or a difference, then I can split the integrand across the things that are added or subtracted. You cannot split an integrand across multiplication or division. It does not work. You can only split it across addition and subtraction. If you have a constant multiplied by the function, like when we had the 3x squared earlier, you can take the constant and pull it outside of the indefinite integral and then find the integral and then multiply the resulting antiderivative by the constant. So you can only split integrals over addition and subtraction. I cannot repeat often enough that you cannot split an integral over multiplication and division. Just keep in the back of your mind that that is what you're going to be spending a large amount of your time in Calculus 2 doing. And in fact, there are entire textbooks called integral tables that go through how to deal with multiplication and division. And you deal with some more of that when you do differential equations. So there are entire courses that deal with just those things. All right. Now, compositions we will deal with this semester, but not until section 5.5, and we'll call it U substitution, where U, of course, is the inside function, as it's been in the past when we did chain rule. So we will learn how to undo the result of composition, but not yet. But we will not do products and quotients. All right. So now we're going to be looking at example 4. In example 4, we have the sum and difference of several different terms. So we can divide this into multiple integrals. Now, I have students ask me, do you have to split it up? And the answer is no. You can leave it all together if you want to. But I want to demonstrate that it can be split up in between each of these steps. All right. Does it have to? No. You can do all of this essentially in your head if you want to, which is what most of you will eventually be working towards: less writing, faster work. Okay. Again, constants can be pulled to the front because they do not depend on x. Anything that depends on x cannot pass through that integral symbol, but the constant doesn't depend on x, so it can. So we have the integral of x dx, and this last one I can write as -7, the integral of dx. Now it looks a little weird to just have the dx by itself down here on the last one. So some students will go ahead and write in a 1 dx just to indicate that there is a constant there. So this is that constant rule. where if you had 2 times x and you took the derivative, you get 2. Now we need to undo that and get back to 2x. So we're going to apply the power rule. So we have 4 tagging along. We take x, we add 1 to the power, and we divide by the new power. This would have a plus c on it. Then we have a minus 5. Then we apply the power rule. 2 plus 1 divided by 2 plus 1, and it would have a constant on it. Plus, now we have x. We're going to do the power rule. The power was 1, so we add 1 to that and divide by the new power plus its constant. And then we have the integral of a constant, which is just x. So minus 7 times, what is going on? Okay. Plus its constant. Now, this will be the first and last time you ever write constants 4 or 5 times. Because what is a constant plus a constant plus a constant plus a constant? It's a constant, right? So taking 4 constants and adding them together, you'll just ball them all together and have 1 plus c. So this is going to become finally 4x to the 4th over 4 minus 5x cubed over 3 plus x squared over 2 minus 7x plus all the constants balled together. And of course, the last thing that I could do is I can take that 4 divided by 4 and write it as x to the 4th minus 5/3 x cubed plus 1/2 x squared minus 7x plus a constant. If you want to check your work, all you have to do is take the derivative of the antiderivative and see if it gives you the integrand. So the derivative of x to the 4th is 4x cubed. The derivative of negative 5/3 x cubed, the 3 comes to the front and cancels. So I get negative 5x squared. Check. The derivative of 1/2 x squared, the 2 comes to the front and cancels the 2. So I get x plus x. The derivative of negative 7x is negative 7. And the derivative of a constant is 0. All right. So to check your work, you just take the derivative of the antiderivative to get the integrand back again.
I have a question.
Okay.
So for the terminology for the integral, you said the argument of the integral is the integrand. So that'd be our 4x cubed.
Minus 5x squared plus x minus 7. That's the integrand. Okay. All right, let's practice on another one. This one is slightly different. So again, you can split it up. You can write this as the integral of e to the x dx minus, you could pull the 3 out, and you could write it as the integral of x squared dx plus the integral of sine of x dx, right? Now the integral of e to the x is e to the x. The inside function is x and its derivative is 1, so we don't have to worry about undoing the chain rule. So we end up with e to the x plus a constant, but we're going to ball all the constants together into one big plus c at the end. And then I've got the minus 3 being multiplied by x raised the power by 1, divide by the new power, undo the power rule. And then I've got to think about this. I took the derivative of something and I got sine. So it's got to be cosine, but that would give me a negative sign. So I need to apply a negative onto the cosine. So this has to be negative cosine of x. The derivative of that gives me sine. And then the next thing we're going to do is combine all of our plus c's together. So we have one big plus c. So we have e to the x minus 3x cubed over 3 minus cosine of x plus c. And then I can cancel the 3's. and I get e to the x minus x cubed minus cosine of x plus c. Now, eventually, your goal is to go from this to this in one step. That's your goal eventually, is to do all the work pretty much in your head, where you go from the original integrand to the antiderivative in one step. That's the eventual goal. But it may take a while. Example 6. Something gives me the derivative cosecant of x cotangent of x. So I can split this one up, and I have cosecant x cotangent of x. The only one that gives me two trig functions is either secant or cosecant. And these are co-functions, so it's got to be cosecant. But cosecant gives a negative, and that's not negative. So that must mean that I multiplied the cosecant by a negative. So this has to be a negative cosecant of x plus, and now let's practice doing it in our head. This is the integral of 3x. And so I'm going to do the power rule on x. I'm going to raise it by 1. 1 plus 1 would give me 2. And I'm going to divide by the 2. And then I'm going to add a big plus c to represent the constant of integration of both. And that's it. And then I would do the derivative to make sure that it gives me back the original integrand. The integral of negative cosecant should be a negative negative, which is positive cosecant x cotangent x. And if I take the derivative, oops, I lost my 3. My 3 went walkabout. So I should have a 3 on there as well. So this should be, bring the power to the front, the 2's cancel, and I get 3x. And the derivative of a constant is 0. Right? Okay, what about example 7? Example 7 is a little bit different. It's not written in power form completely. We have a square root and it's being cubed. So the first thing we need to do is write it in power form. So we're going to take this integrand, which is the square root of x being cubed with respect to x, and we're going to rewrite this as x to the 1/2 power. That's what the square root is, cubed. And the differential is dx, which becomes x to the 3/2 power with the differential dx. Once you have it written in the power form, it's pretty simple to do. You simply are going to add 1 to the power and divide by it. However, adding 1 to the power means you need a common denominator. So the best thing to do is use that denominator and add 2 halves to it. And so then we're going to divide by 3/2 plus 2 halves plus a constant, which gives us x to the 5/2 divided by 5/2. And because of the division by a reciprocal is multiplication by the number, or you can use the denominator if the denominator is the numerator, you end up moving this up to the numerator. My c keeps erasing. So this gives us 2/5 x to the 5/2 plus c. If you want to reinterpret it in terms of radicals, this would be written as 2/5 the square root of x raised to the 5th power plus c. And I would take either one. In fact, I think in a lot of ways it's easier just to leave it in the power form. So you're welcome to leave it in the power form. Now, I put example 8 in here, mostly because I've discovered over the years that students just get a little weirded out when there's no expression other than a constant in the integrand. And I want to make sure that you realize When it's just a constant, it just becomes the constant times x. So this is not anything unusual or special. It's just the normal constant times the differential, which you can think of as the constant times x to the 0, since that equals 1. And then you can do the power rule on it, which gives you -1 x to the 0 plus 1 divided by 0 plus 1 plus a constant, which gives you -1 times x. Or you can just write it as -x plus a constant. Right? So don't get weirded out if it's just a constant with the differential. It just becomes the constant times x, or whatever the variable of integration is. Okay, so for example, let me give you one more example. If you have 5 dt, your result is going to be 5t plus a constant. The variable of integration is given by the differential. So if this is dt, then the variable has to be t. Right? Let's take a moment, everybody work on this one on their own, and then we'll come back together and see what you got as a result. And if you get number 9 and you're waiting for us, you can go on to number 10. All right, let's take a look at this one. You can split it into 2 separate integrals because you have subtraction. Remember, you can only split across addition and subtraction. Multiplication and division are absolute no-nos. Huge colossal error, as in like no partial credit at all errors. So then we apply the power rule. X to the 1/3 plus 3/3 divided by the new power minus x to the 2/3 plus 3/3 divided by the new power. And then we can combine the power. So 1/3 plus 3/3 is 4/3, and then we divide by 4/3. Dividing by 4/3 is the same as multiplying by 3/4. And then we have 2/3 plus 3/3, which is 5/3. Dividing by 5/3 is the same as multiplying by 3/5. Don't forget the plus c. I am a stickler for the differential, and I am a stickler for the plus c. It is the major difference between a definite integral and an indefinite integral. We're only learning the indefinite integral right now, but we'll be learning the definite integral next week. Let's take a look at this one. This one is a little tricky to start. What makes this one work, because originally you see division here, and I told you, you cannot split the integral between division. So you've got to do something to get rid of the division, or you can't do this problem. And what makes this work is you've got a binomial divided by a monomial. So you can split it into 2 fractions and reduce the fractions using power notation. So what I'm going to do in order to make this work is I'm going to have 3x squared divided by x squared plus 2 divided by x squared. I'm splitting the fraction into 2 separate fractions with a common denominator. Then I'm going to rewrite each one of them using power notation. Now x squared divided by x squared cancels, so the first one becomes the integral of 3 dx. The 3 could be pulled outside if you want to. And then the next one is 2 divided by x squared, but I can instead write it as 2x to the -2 dx. Now, again, you could pull the constants out and have the integral of 3 times the integral of dx plus 2 times the integral of x to the -2 dx, right? The only one that you cannot undo the power rule with is 1 over x, or x to the -1. That's the natural log of the absolute value of x. So now that we have this, we have 3 times a constant times dx, which is going to give us 3x. And then we can undo the power rule. Don't get messed up. It's the same rule. Add 1 to the power, divide by the new power. And don't forget your plus c. So this gives us 3x plus 2x to the negative 1 divided by negative 1 plus the constant. And then we can rearrange the second term, pull the negative to the numerator and drop the x to the negative 1 to the denominator as x. So this gives us 3x or minus 2 divided by x plus c. And I think that's probably the best way to leave it. You can also leave it with x to the negative 1. I think that's valid as well. We're now ready to talk about what are called initial value problems. Initial value problems are something that comes up in differential equations. So the courses that you take after you finish Calculus 3, and you may be going, oh my God, I'm doing something that advanced. Yeah, you are, okay? This is sort of where differential equations start, where differential equations means you know something about the derivative, but you don't know the original function. So in this case, we know something about the derivative and we know maybe a point on the original function, but we don't know what the original function is. Can we find it? It could also be something like, you know the acceleration function, you know the initial velocity, you want the velocity function. So you take the antiderivative acceleration to undo the derivative to get back to velocity. But it'll only give you velocity up to a constant, and then you use your initial value of the velocity to pin down what the c is. So this is a way to actually find out what the true value of that constant is in that particular problem. So when we're looking at these, we'll often talk about a point x naught, y naught, and we'll often call this the initial value. In other words, the value at the first moment in time or the beginning of the problem. And sometimes we write it like this, which looks kind of weird, where y as a function of x is actually equal to some f of x, all right? In differential equations, it's more common to use y as the variable than it is to use lowercase f. This is called an initial value problem. When you know something about the derivative and you know an initial value, it's called an initial value problem. Sorry about that. The dog's going berserk. Somebody must be walking around the street. Okay, so we're going to take a look now at example 11, and we're going to solve what is basically an initial value problem. So when we're looking at this one, we know that the derivative of y with respect to x is 3x to the negative 2, and we know a point on the actual function. Our job is to find y as a function of x. We know the value 1, 2 is on the graph of y, and we know the derivative of y with respect to x is 3x to the negative 2. So what we're going to do is we're going to take the antiderivative, which is going to give us 3x to the negative 2 dx, and we're going to find what that antiderivative is so we can get back to the original function y. So this gives us 3 times x to the negative 2 plus 1 divided by negative 2 plus 1 plus a constant. Now, when we rewrite this, negative 2 plus 1 is negative 1. So we get 3x to the negative 1 divided by negative 1 plus a constant, which becomes negative 3 over x plus a constant. And this is giving us y of x. Now, I want you to take that initial point and plug it in and see if you can figure out what the constant c is. Okay, does anybody have a value for the constant that they would like to volunteer?
5.
Okay, Jean said he got 5. Roz, what did you get? 5. Any other people who got a value? So we have y of x. Okay, Caleb agrees. Cherie says 5 as well. So we have y of x is negative 3 over x plus c. And then we know that the y value is 2 when x is 1. So from here, we say the y value 2 is equal to negative 3 over 1 plus a constant. And that tells us instead that 2 equals negative 3 plus c, or c is equal to 5. And then the last thing we do is we rewrite the equation with the constant in it. And that becomes our actual equation for this particular problem. So it's an initial value problem, and that's the value that we had, that we were given, 1, 2. We have one more to work, which is this one right here, solve the initial value problem. This time, instead of using dy dx, it's written in the form of f prime of x is equal to this expression. And we know that we have an initial value that f of 0 is 0. So our point here is 0, 0. And this, of course, represents the derivative of f with respect to x, which is equal to that expression. So we want to undo that by taking the integral. And we're going to do it with respect to x. Now we do it with respect to x. This is actually an assumption we're making because the only variable present here is x. It is an assumption. Normally you need to be told, but we can assume that the only variable present is the independent variable. So we take the antiderivative function, which eventually you'll do it all in one step without splitting it up, but you can split it up and you can take out the constants. But the variables have to stay behind inside the integrand. Anything that depends on x cannot be pulled out past that integral symbol. If it has x at all, it cannot leave the integrand. It has to stay inside. So this will give us x to the 4th over 4 minus 8x to the 3rd over 3 plus 16x squared over 2 plus x plus a constant. We can simplify this by writing it as 1/4 x to the 4th minus 8/3 x cubed plus 8x squared plus x plus c. Now we're told that when x is 0, y is 0, and this represents our function f of x. All right. So when we take the antiderivative of the derivative, we get the function back again. And this is our f of x. If x is 0, then all the terms that have x in it will drop out and you just get the constant. So the constant would be 0 equal to 0. So f of 0 is 0, which equals 1/4 times 0 to the 4th minus 8/3 times 0 to the 3rd plus 8 times 0 squared plus 0 plus c, which means that 0 equals the constant. And that means that our final function is the expression 1/4 x to the 4th minus 8/3 x cubed plus 8x squared plus x plus c. Now, this is the end of the section on antiderivatives. The next thing that we're going to do is we're going to start looking at what a definite integral will be by examining Riemann sums and the area under a curve. So that's what's coming up next.